Okay, good afternoon, everybody. For anybody who doesn't know me, my name is Cathy Ramsbottom, and I'm from Queen's University in Belfast. And it's my pleasure to be here today to talk to you on the topic of electron impact excitation of astrophysically important open D-shell ions. And I would like to thank the Icpeac committee for selecting me to give this presentation. Okay, let me first introduce you to our group at Belfast. There's myself, and a new addition to the group who's just recently joined us is Conor Balance from Auburn University. And we're really happy to have Conor back in Belfast. The Belfast boy has come home. We also have Professor Alan Hibbert. Although he's retired from the field, he's still very active in this area. We have a close collaboration with Daresbury Laboratory in the UK. And we work very closely there with Phil Burke and Val Burke and co-workers. And then I have what I call my additional children, my postdocs and PhD students. So we have Shibashis Leha, Niall Tyndall, who is here somewhere in the audience, Stephen Spencer, and Michael Turkington. So as a group, what do? Well, we specialize in the generation of atomic data, accurate atomic data, for use by astrophysicists and laboratory plasma physicists. I like to consider it as an analogy that you're baking a cake. We provide the ingredients for the cake in certain quantities. Then we join with the astronomers and the plasma physicists, and we process these ingredients under certain conditions, and hopefully at the end of this process, we have something that's beneficial to both groups and quite satisfying. So we generate quite a lot of atomic data. I've listed quite a bit of it here. For the bound levels of our atoms and ions, we calculate energy levels, wavelengths, lifetimes, oscillator strengths and transition probabilities for transitions between these bound states. And the collision process that I'm going to concentrate on today is the electron impact excitation. The electron impact excitation of a specific group of elements, the open D shells. Associated with these collision strengths for this collision process are the effective collision strengths, which is what the astronomers will use in their applications. Also at Queen's, we look at other collision processes. We calculate the photoionization cross-sections, level resolved photoionization cross-sections for both ground and metastable levels. And if we have to, we look at recombination rates, both dielectronic and radiative, and some proton rates as well. So all of this atomic data can be used in complex modeling codes around the world. And what they're basically doing is they are analyzing and modeling astrophysical spectra. So that is what we do. So what are these open D-shell ions that I talked about in my title? Well, they lie here in the periodic table from Z equals 21 scandium right through to zinc, Z equals 30. So if we consider a light atomic system to have an atomic number of Z less than 30, so we're right on the cusp, just below that. Now, these particular species are very important because they are observed everywhere in astrophysics, particularly in their low ionization stages. So you will see lines of these open D-shell ions in astronomical objects as diverse as the Sun and other stars, gaseous nebulae, active galactic nuclei, Seyfert galleries, quasars, supernova remnants, and supernova. So the scandium here will have an open D-shell 3D1, 3D squared, 3D cubed, and so on and so forth. So these are the ions we're particularly looking at. Now, what I've put up here is the latest version of the Chianti database. Now, Chianti is where we, as atomic data providers, will put our atomic data for download by the astronomers and the plasma physicists. So this is the latest version, and you can see for many ions, there's a huge amount of data available. Here, this nice white area here, you'll see that there's no atomic data for our iron peaks or our open D shells. Here's scandium, titanium, vanadium, chromium, manganese, iron, and so on and so forth. Very little atomic data available. Iron is quite well represented, but that's due primarily to the huge effort that was made by the Iron Project and its members over the year. So what's the problem? What's the problem with these iron peaks, and why are they so difficult? to calculate. I have put up here the term diagram of one of the iron peaks, iron 2. This is the so-called Rosetta Stone element. And basically, it is the most observed, the most requested, the most wanted atomic data that we would get as producers. I've presented the term energies in terms of manifolds, so configuration terms. Here, centimeters to the -1, and here is EV. So the ground state of iron 2 is a 3d64s, an open 3D shell, and that is a configuration that it shares with 23 other LS terms. So all of these 24 terms lie below 10 EV. Now, you're not going to model an ion with one specific configuration. You've got to add a few more. So the next term up is a 3D7, and there are 8 of those. But one of the problems that we have with these ions is that these manifolds are not nicely separated. These rectangles are all on top of each other, so all these levels will be intermixed. Then we have the 3d5-4s squared, and then here's where the first odd states start to come in, the 3d6-4p and the 3d5-4s-4p. So if you want to model iron 2 below this 10 EV mark, you would have to include these 5 configurations. These 5 configurations give rise to many hundreds of bound states, which have to be incorporated into our configuration interaction expansion. So that's the first problem, many hundreds of target terms. These hundreds of target terms will give rise to thousands of coupled channels, and this makes things computationally difficult. And finally, what we're calculating is a collision cross-section. In this cross-section, there will be many Rydberg resonances converging onto these target states. They're very narrow, they all have to be resolved, so you need many thousands of energy points. So you have many hundreds of bound states, many thousands of coupled channels, and many tens of thousands individual energy points. Now, there are many methods out there for calculating the atomic data. One of the most powerful and most reliable is the OR matrix method. Now, in 25 minutes, I'm not going to go through the theory of the OR matrix method with you. So just very briefly, configuration space describing the collision is divided into 2 regions, an internal region and an external region separated by this radius R. The boundary between internal and external is called the OR matrix boundary. In the internal region, the scattered electron here is within the charge distribution of your target, so your wave function expansion is quite complicated to set up. In the external region, this electron has moved away from the charge distribution of the target, so the physics is simpler. So internal region, complicated. External region, less complicated. The boundary is the match between the two, and this is where you form your OR matrix. So your OR matrix is the pivotal collection between internal region and external region, and it is an energy-dependent observable. Now, the OR matrix method at the moment comes in many forms, many variants, both serial and parallel. I've listed them here. The very early OR matrix was done in LS coupling by Keith Barrington way back in 1974. So I've put it up here just because it deserves to be there. Nobody wants atomic data in LS coupling anymore. All the astronomers want transitions between the fine structure states. So we need to include relativistic effects. So we have the variant of the Bright-Pauli OR matrix, where the one-body terms are included in the Hamiltonian of the total system. So we have the mass correction, the Darwin, and the spin-orbit term. So we call this kind of a semi-relativistic approach. Then we have the fully relativistic dark, where all the one- and two-body terms are included in that Hamiltonian. So it's a fully relativistic calculation. On top of this, we have 2 what we call transformation methods. Now, there's the one which is called OR matrix 2, and that was developed by Phil Burke, the late Cliff Noble, and Andy Sunderland in Daresbury in collaboration with Queen's University. And then you have the ICFT method of Badnall and Griffin. Both of these transformation methods are really similar in that both of them treat the internal region in LS coupling only. So no relativistic effects in the internal region. Relativistic effects are incorporated into the less complicated external region via a frame transformation. So no relativistic effects in the internal region, so we can work that complicated area more simply. There are subtle differences between these 2 transformation approaches in that Or matrix 2 will transform the surface amplitudes, which are energy independent, whereas ICFT will transform the energy dependent on physical K matrices. But the similarities between the two outweigh the differences. Finally, just to complete the picture, bright Pauli, dark, or matrix 2 and ICFT all use an orthogonal orbital basis. But there is no physical reason why you should have to do this. So we also have the B-spline OR matrix, which doesn't use an orthogonal basis. It uses a non-orthogonal B-spline basis in the internal region. But the OR matrix technique of internal and external region is exactly the same. So the first thing that I want to show you in this talk is that for these very difficult, important iron peak ions, it really doesn't matter which of these variants you use and whether you use them in serial or parallel. You should get good results if you use the codes in the right way. So what I have here is one of our atomic data. It is the collision strength. So I'm plotting here the incident electron energy against the collision strength. And the first thing that I want you to notice is all of these Rydberg resonances, very narrow, converging onto the target state thresholds. And these are what I said earlier that we need to resolve, which is why you need tens of thousands of energy points. I think there's about 20,000 energy points on this graph alone. So we're looking at an open D shell ion here, chromium-2, ground state 3d5 sextet F5 halves. This calculation was done by Ian Wasson back in 2010. And it was a really large calculation. It had over 280 fine structure levels in it. It was an OR matrix 2 calculation, so it was a transformation. So we used LS coupling in the internal region and then performed that transformation. We have redone this calculation using the bright Pauli, so the same model, and you can see that the resonance profiles are all sitting nicely on top of each other. And the background as well looks good. I should say here that this OR matrix 2 calculation was done on our local node back at Queen's University, whereas we had to use high-performance supercomputing at NERSC to do the bright Pauli calculation. But there's very little difference. Now, these collision strengths, astronomers don't want them. There's far too many data points on this graph. What they want is a smoothing over all these resonances. So we Maxwellian average over the resonance features to form the effective collision strengths. And I have on this graph here a plot of the effective collision strength against the electron temperature in Kelvin. And the effective collision strength that corresponds to that collision strength that I showed you on the previous graph is this one here. And again, you see when you average over all the resonances, bright Pauli and the transformation OR matrix 2 give really good agreement. And just to show you that it wasn't a one-off, that we can find hundreds of these transitions that give you the same agreement, here's transition 1 to 3, 1 to 4, 1 to 5, and 1 to 6. So let's look at another iron peak, manganese 5, slightly higher ionized, Z equals 25. This was a smaller calculation done by Meredith Grieve, and the paper is still in preparation. We're doing the modeling for this at the moment. It was an 80-level calculation, and we used 3 of the OR matrix variants. We used the transformation ICFT code, the bright Pauli, and the fully relativistic dark. And again, you can see that the resonance profiles agree really well across the incident energy range. And if we Maxwellian average over this, you will see that the effective collision strengths all agree to within 10%. And again, you can do this transformation ICFT on a small local computer or your desktop, whereas these ones need substantially more computing facilities. And just not to leave out the B-spline OR matrix, I've got a comparison here. Now, technically, I'm cheating because this is not an iron peak ion. It's magnesium 8, but it was all I really had for the comparison. So we're looking at a low-lying transition. And again, you can see that the bright Pauli and the B-spline OR matrix agree really well across the resonance region and the background cross-section as well. So we're fairly happy that any of the variants of the OR matrix code will give you the same results for these iron peaks, and that people with less facilities than others, you don't have to have access to high-performance computing to get some good results out of these codes. Now I want to go back to iron 2, this Rosetta Stone element, the most observed of the iron peaks. And I love this figure. It was given to me by Professor Gary Furland, the author of Cloudy. And what we have here is 4 astrophysically important ions: hydrogen, magnesium 2, and carbon 4. And if you look at hydrogen, you'll see all the bound states are all nicely separated, converging onto the ionization limit, a really nice ion to model. Same with magnesium 2, carbon 4. These ions where all the manifolds are nicely separated. This is iron 2. This is the beast that we're trying to model at the moment. And those bound states form like a pseudo-continuum of bound states all on top of each other. Many of them have a different configuration. Many of them are degenerate. So it's really, really hard to model this. So what I'm going to try and do now is show you with numbers how, as you add more and more of these horizontal lines or bound states, how these calculations can escalate computationally. So what I have here is the number of configurations. So as I add an additional configuration, what happens in both LS coupling and in the intermediate J-pi coupling? So if I only include the ground state configuration, 3d64f, I have those 24 LS states. I add the next configuration, 3d7, I go to 32, 100, 116, and here I have the associated number of coupled channels. So all of these numbers are not bad. We can actually work with this quite easily. You can't really say the same thing when you start with relativistic effects straight away and you work in J-pi coupling from the start. The number of target states increases really quickly, and very quickly the number of channels becomes computationally far too great for us to cope with. If you look down at the bottom table down here, I've taken two of these calculations. This one with 100 LS states or 262 fine structure, and to show you computationally what we have to do. In LS coupling, if we have those 100 states, we've got to diagonalize a Hamiltonian matrix of maximum size, about 12,500, and we're dealing with about 5,000 individual transitions. That exact same calculation, but now in J-pi coupling, means we have to diagonalize a Hamiltonian matrix of about 36,000, and we're looking at about 35,000 individual transitions. If I look at one of the other models, even bigger, this 5 configuration model, where I'm including 1, 2, 3, 4, 5 configurations, 716 fine structure levels, gives me over 5,000 channels, Hamiltonian matrix sizes of greater than 100,000, and over 250,000 individual transitions that we have to look at, which is a bit of a file management issue for us. So looking at the same table again, the ones in red we have completed. So we've done this calculation in LS, we've done this calculation in J-pi, and that's the biggest data set that's available at the moment, and this is the one we're working on. Now, we've never actually done a calculation with that many coupled channels before, but the one in blue is the one that we're progressing with at the moment. Okay, there have been many calculations done for iron 2 over the years, from way back in the 1980s. None of them agree at any temperature, particularly for the low-lying forbidden transitions. So I've put here the lowest transition for iron 2. So we've got from the ground state, the 3d64s sexed at d9 halves, to the first split level of the ground state, the 3d64s sexed at d7 halves. Now I'm working with effective collision strengths here, so we don't have all those resonance profiles interfering. So it's electron temperature against the effective collision strength. All the calculations are here, the best that's available at the moment. This is a calculation by Zhang and Pradhan in '95, and it was a transformation, an early transformation calculation. This is my data here in black, and it was a bright Pauli calculation. And here in blue, we have a very early calculation done by Keith Barrington in 1988. It's a very small calculation, but it was a bright Pauli calculation at that time. And then finally, the most recent results of Bautista et al. It's a 53-level calculation, and it's here in green. These ones here are interpolated results of Keenan et al., so they weren't a specific collision calculation. They were just interpolated from the Keenan data. So 10 to the 4 is the temperature of maximum abundance for iron 2, and you can see that there's about a 50% difference here between the data points at that temperature. They do seem, however, to be kind of gathering together in groups. Here, these two calculations are agreeing really well, and these three up here are agreeing really well. And what's interesting is the difference between these two models is that these two only include even states. There are no odd states at all in these calculations, whereas these ones up here actually do include both even and odd target states. 1 to 3 gives exactly the same picture. At 10 to the 4, there's very little agreement between all of the calculations. So what we wanted to do is we wanted to model this. We wanted to simulate iron 2 using one of the modeling codes and just see how these differences manifested themselves in the spectral analysis. So we've used Cloudy. Now, I don't know if anybody's used Cloudy, but you need 3 different types of atomic data. You need energy levels, you need A values, and you need these effective collision strengths. So when I approached Gary Furland first with my 262 model up here, I said to him, Gary, I've got a new data set here for you, will we model it? And he said, Kathy, I already have a 371 model in Cloudy. It's bigger, it's better, so I don't think this 262 is going to do any difference. So the model in Cloudy at the moment includes this Zhang and Pradhan data, which you can see only includes 142 levels. Both of these calculations include 3 configurations. Both include even and odd target states. But the difference in number here between the 142 and the 262 is that Zhang and Pradhan only included sextet and quartet levels, whereas we include them all, doublet, sextet, and quartet. And I think there's a couple of octets in there. Now, I can understand why they did it, because if you're only looking at transitions between a sextet and a quartet, you only have to put in the quintet spin states, which computationally makes your calculation a lot smaller, whereas we have the 1, 3, 5, 7, and 9 spin states in there. So we put both of these into the Cloudy model, and this is what we got. And it was really surprising. It was really surprising because everyone considers bigger is better, but the smaller model, which is in blue, using our 262 model, gives you far more emission lines than the larger 371 using the Zhang and Pradhan data. And this was really surprising. So what we did was we investigated this further, and we used some ADAS software, which allowed us to predict the top 50 iron 2 lines in a particular wavelength, so the strongest iron 2 lines. And what we found is between these 2 wavelengths, 2000 and 3000, we find that the strongest, the top 50 lines, all came from transitions that involved either a sextet or a quartet level. Not one of the top 50 incorporated a doublet level. So all of these levels were actually in the Zhang and Pradhan model. When we went to 3000 to 4000, 8 out of the top 50 involved a doublet level. And by the time we got to 6,000, 7,000 angstroms, 30 out of the top 50 involved a doublet level. So the conclusions we draw is that a bigger model is not necessarily a better model, but a more complete set of atomic data where you have included all the bound states for a particular configuration seems to be more important and seems to actually predict more emission features. This is the same figure here, except I've separated the 2 models for a clearer representation. Now, the sad thing about the whole thing is that neither of these 2 models, the 262 or the 142, is actually big enough to do a lot of the modeling that we actually want to do. This, and I'm sorry if this is a bit blurry because I snapshotted it from a paper. This is a paper by Karen Leckie in 2007. And what they're doing here is observing a high luminous quasar, PHL 1811. Now, quasars are very interesting astronomical objects in that they are objects which are the most distant that we can observe. So the light that we're seeing coming from these quasars was emitted so long ago that the universe was actually quite young, about 1 gigayear. So these quasars are very important probes of the early universe, and in particular the onset of early star formation. So what this figure is here, up here at the top, you have all the bound state energies of iron 2, and they're kind of color-coded according to their transition probabilities. But you can see that there are bound states of iron 2 up at about 15 eV that are contributing to quite strong emission features in the spectra of these high luminous quasars. The bottom one is the corresponding one for iron 3, which is another important iron peak. And again, you can see that there are very strong emission features being predicted by bound states as high as about 19 eV. Now, if I go back to my energy level diagram and my manifolds, the best calculation at the moment includes this one, this one, and the odd states here. That's your 100 level, 262 fine structure level calculation. The highest energy we go to is about 11.8 eV. So this model is actually not big enough to do the spectral analysis for the quasars. We need to include more terms. Putting this one in will give us more bound states, but it won't actually increase our energy. Putting this one in, though, will give us bound states up at about 23 eV, which is highly appropriate for the modeling of these luminous quasars. So this is the calculation. This is that blue one that I talked about, the 716 levels with the 2.5 million transitions and the Hamiltonian matrices of greater than 100,000. This is the one that we're doing at Queen's at the moment, and it's specifically to model those quasars. So the latest calculation from QUB includes these 716 JPI target states from these 5 configurations. The last target threshold now goes up to 23 eV, which is highly applicable for these recent quasar studies. We've decided to do a bright Pauli or a dark calculation, and the reason we've decided to do this is because we have HPC time on a big machine in Germany. So we have thousands of processors available to us. So we thought we might as well do a relativistic calculation. It's well underway at the moment, so it is. The internal region is completed. We are in the external region. And this is where I'd love to say, da-da, my next slide is the definitive results. But I can't because my jobs have been sitting in a queue for nearly a month now on that machine. So I guess everybody's trying to get data through for conferences. So this calculation is really close to completion. And I hope that the next time I'm talking to you on this topic, we will have all the ingredients for our cake. We will have done the mixing of the ingredients, and hopefully we'll have something nice for afternoon tea. So thank you very much for your patience.